The James Webb Space Telescope has uncovered a massive, mysterious structure that's forcing scientists to rethink how galaxies form. Until recently, the prevailing belief was that spiral galaxies developed slowly over billions of years. But the discovery of the colossal, big wheel galaxy suggests we may have been completely mistaken. How can this be? How could a galaxy become significantly more massive than our Milky Way just 2 billion years after the Big Bang? And that's not the only puzzle astronomers are facing. New findings indicate that dark energy, the mysterious force driving the universe's expansion, may actually be weakening. This revelation could even challenge the foundation of modern physics, including Einstein's theory of relativity. Curious about what the James Webb Space Telescope has discovered and why it's once again challenging our understanding of the cosmos? Stick with us until the end to find out. In many ways, Webb is turning science fiction into science fact. Its observations have revealed the existence of cosmic objects we once thought couldn't possibly exist. Among the most astonishing are colossal galaxies that formed just a few 100 million years after the Big Bang, yet they're already as massive as the Milky Way. And that's a serious conundrum. According to current models, there simply wasn't enough ordinary matter that early in the universe to build such star-packed giants. The result? A deepening mystery for astronomers everywhere. But now, the Webb telescope has revealed something that makes even this colossal mystery seem like a minor detail. Here's the twist: this so-called big wheel galaxy existed just 2 billion years after the universe began, yet it was already the size of our own Milky Way and 5 times as massive. In light of that, it's no surprise that this baffling structure is once again challenging our understanding of how the cosmos evolved. And here's the ironic part: we have pure chance to thank. The research team, led by Viking Wang of the University of Milan Bicocca, wasn't actually searching for gigantic, improbable galaxies. They were simply using Webb to study a distant quasar and the supermassive black hole at its core. While analyzing the image, which also captured the region surrounding the active galactic core, scientists noticed something unexpected. In the image's left corner appeared a massive spiral galaxy with remarkably prominent arms. When they calculated its redshift, they discovered the galaxy's light had traveled for about 11.8 billion years to reach Earth. That means this galaxy already existed when the universe was only about 15% of its current age. Named the Big Wheel and featured in Nature Astronomy, the galaxy was found, using data from the James Webb Space Telescope, to span approximately 100,000 light-years, making it comparable in size to our own Milky Way. Researchers also studied its rotational dynamics and found it spins at incredible speeds, with the velocity increasing as you move outward from the center, reaching several hundred kilometers per second. Interestingly, its rotational speed aligns with the Tully-Fisher relation, a well-established connection between a spiral galaxy's brightness and how fast it rotates. This enables scientists to estimate its distance. In essence, the Big Wheel is not only among the most massive star clusters ever observed in the early universe, but its structure and features also closely resemble those of the largest, most evolved spiral galaxies we see today. So how did the Big Wheel grow so massive, so quickly? How could that even happen? Typically, astronomers believe that spiral galaxies form slowly over extended periods, either by drawing in gas from their surroundings or through mergers with smaller galaxies. However, such rapid mergers are usually thought to disrupt spiral patterns, turning them into more chaotic shapes. Yet, the Big Wheel seems to have defied this expectation, expanding swiftly to an immense size while remarkably preserving its elegant spiral form. What's equally puzzling is that, despite its enormous size, the Ferris wheel galaxy is growing at about the same pace as other galaxies from the same period in the universe's history. What makes it even more intriguing is the setting in which it formed. This galaxy resides in an unusually crowded region of space, so packed that galaxies are practically brushing up against one another, in an area 10 times denser than average. In fact, scientists think this tightly packed environment may have played a key role in the Ferris wheel's remarkable growth. It's likely the galaxy experienced a series of gentle mergers, allowing it to keep its graceful spiral disk intact. On top of that, the gas flowing into the galaxy seems to have aligned perfectly with its rotation, helping the disk expand rapidly without being thrown out of sync. Together, these conditions created the perfect storm for galactic development, and gave us a truly extraordinary cosmic discovery. In the end, the discovery of the big wheel was nothing short of extraordinary and highly improbable. Statistically, models estimate the likelihood of finding such a structure in a survey to be less than 2%. Astronomers likely succeeded only because the big wheel happened to be located in an unusually dense region of the universe, an environment drastically different from what we typically observe. But the mystery doesn't end with its origins. The big wheel's future also raises intriguing possibilities. Given its crowded cosmic neighborhood, it's plausible that more galactic mergers could occur, potentially evolving this already massive structure into an even larger galaxy. So, what's going on with the cosmological constant? While the big wheel presents a fascinating challenge on a galactic scale, the next discovery strikes at the very heart of our cosmological understanding. To grasp this, let's recall that the universe has been expanding at an accelerating rate since the Big Bang, a process thought to be driven by dark energy. According to the Standard Model based on Einstein's theory of relativity, this dark energy should have a constant density throughout time and space, hence the term cosmological constant. At least, that's what we believed. But recent astronomical data has started to challenge that view. Observations suggest that the universe is expanding faster than the Standard Model predicts. More surprisingly, new evidence indicates that dark energy might not be constant after all. Now, the Dark Energy Spectroscopic Instrument, DESI, has added even more weight to this growing suspicion. This experiment, based in Arizona, was specifically created to study dark energy, one of the most mysterious forces in the universe. Using the DESI instrument, scientists have now mapped over 15 million galaxies and quasars, producing the most detailed 3D map of the universe ever made. To better understand dark energy, the DESI team didn't just look at the redshifts of galaxies and quasars, they also examined faint patterns in how galaxies are distributed, known as baryonic acoustic oscillations, or BAO. These BAOs are remnants of sound waves from the early universe that influenced where galaxies and galaxy clusters formed. By measuring the distances between these patterns over time, scientists can trace how fast the universe has expanded, and gain insights into how dark energy has evolved through cosmic history. Recent mapping results now strongly suggest that dark energy's influence isn't constant as once believed, instead, it appears to have weakened over time. When combined with data from other surveys, the deviation from the Standard Model reaches a significance level between 2.4 and 4.2 sigma. As the researchers explain, at 4.2 sigma, we're approaching the point of no return. Multiple independent datasets are all pointing in the same direction. The evidence for evolving dark energy is becoming more compelling than ever. This so-called point of no return refers to the 5 sigma threshold that physicists consider the benchmark for confirming a discovery. So what does this mean in practice? Essentially, the DESI results challenge a core assumption of the standard cosmological model. The idea that the cosmological constant is truly constant may no longer hold. In the most extreme scenario, this could suggest that our current understanding of the universe, and Einstein's theory of relativity, may not be entirely accurate. DESI spokesperson Will Percival remarked, "It's increasingly clear that we might need to revise our standard model in light of these findings." Could it be time to consider alternative models to dark energy? Such theories do exist, with some proposing that the strength of dark energy, or even gravity, varies depending on factors like matter density, scale, or time. However, the DESI team found that most of these alternative models don't align well with their measurements. The exception lies in a subset of theories that involve what's called a phantom crossing of dark energy. This phenomenon suggests that dark energy's influence has shifted over time, crossing the value predicted by the standard model, being stronger at some points and weaker at others. Still, it's premature to declare the end of the standard model, as the current deviation sigma value isn't yet statistically significant enough to warrant such a conclusion. That said, the findings are enough to make many experts question some foundational aspects of our cosmological framework. Looking ahead, scientists hope that further theoretical developments, as well as data from the European Space Telescope Euclid, will provide clearer insights. Like DESI, Euclid aims to probe dark energy and dark matter in unprecedented detail, helping us identify where our current models may fall short.